Hello, my name is Ryan Rayshek. I'm joined with Joe Whitney and Michael Sprar, and today we are going to discuss SIFT, ORB, and YOLO for object detection.
The first algorithm we will discuss is the scale invariant feature transform, known as SIFT. SIFT extracts points of interest from an image known as features. These features can then be compared to other images to try and identify if the same object is present in another image. SIFT is special because it has the ability to extract features that are both invariant to changes in scale and in rotation. There are four major steps in completing the SIFT algorithm, and each will be looked at independently. The first step is creating a new space for these images, known as the scale space, which is a set of scaled up and scaled down versions of the original image. From this space, points of interest can be found using the difference of Gaussian method. The first step in this process is scaling the input image down and progressively blurring the scaled images using the Gaussian blur function, which can be seen at the top of the slide. Next, one blurred image is subtracted from an image with a different blur on the same scale to create a brand new image. This process results in a set of new images where the majority of the noise has been removed and contains only the key features such as the edges of the object in the image. With the new set of images, we can now identify which key points should be kept and which should be discarded in the key point localization phase. To do this, the extrema between the resulting difference of Gaussian images are found. This is done by comparing a single point on one image with its neighbors on the same scale, but also by comparing this point to the neighbors on the scale above and below. From here, only the extrema are kept as key points, and these key points are in turn scale invariant. The next step in the algorithm is to make the features rotation invariant. This is done by assigning each key point an orientation. To do this, the gradient in the x and the y is calculated for both the key point and the surrounding pixels. Next, the magnitude and orientation is calculated using the equations at the top of the slide. Then these magnitude values are placed in a histogram that contains 36 separate bins, where each bin represents an orientation angle between 0 and 360 degrees. So in our example, a value of 16.64 will be placed inside the 50 to 59 degree angle bin. Finally, the bin with the largest value will be selected as the overall orientation of that key point, hence aiding in making the key point rotation invariant. The last step is making a descriptor for the key point. This makes larger groups around the key point to capture important aspects over larger areas. By first taking a 16 by 16 section around the key point, dividing that down further into 4 by 4 blocks, and creating another histogram based on the magnitude and orientation. These values are placed into another set of bins where each arrow represents a bin. So in our example, there are 8 bins, and the size of the arrow represents the magnitude. This produces a descriptor for the area around each key point, and hence the algorithm has been completed. With the algorithm understood, we can now look at some of the advantages. The first is that the features are both rotation and scale invariant, which makes object detection easier. This can be seen from the output image on the bottom right, which is a result from my code that implements this algorithm. This example shows that even though the Tide bottle is rotated and smaller than my training image, SIFT was still able to identify the key points and find the object in the image. Finally, SIFT is relatively easy and quick to implement in Python. Some disadvantages of SIFT is that it is slower than ORB and is not as precise as neural networks. Additionally, SIFT struggles when there are changes in lighting over the image. And finally, there are thresholding values that need to be played with in order to get the best results. As an example, in the image to the right, I lowered the threshold value, and in turn, false positives were found. This aspect of SIFT may make it hard for engineers to use as an object detection algorithm, because even though a certain threshold may work for most images, it may not work for all. But if the threshold value is lowered, more false positives might arise. So now we will see an example of the SIFT algorithm in action. So as I run the code, our training image is over here and our query images are on the right. So as it loops through these images, it's looking for key points from the fish in these objects in the query image directory. There it is, and it finds it. So if we continue, it is also able to find the object within a separate image.
The next algorithm our team looked at was ORB, which stands for Oriented Fast Rotated Brief. It's similar to SIFT, however, it's more robust and computationally more efficient. It utilizes fast key points and brief descriptors for its matching and detection. The first part of the ORB algorithm are the fast key points. Key points are used to match one image to another, and there are many different ways to define how to find a key point. In the upper right-hand corner of the screen, you'll see an example of how the algorithm of FAST determines if a pixel is considered a key point. Basically, what's happening is the code will take a pixel and compare the brightness level of the pixel in the surrounding ring, and if there are 8 or more of the pixels that are greater than some threshold value for being brighter or darker, then it is considered a key point. The issue with these key points is they don't give any information about scale or rotation. Thus, we can use a multi-scale image pyramid to do the key point detecting at various resolutions so that the key points become scale invariant. Additionally, we want the algorithm to be rotationally invariant, so we utilize the intensity centroid with some handy math as seen in the lower part of the screen to find the orientation of the key point. The second main section of the ORB algorithm is finding the brief descriptors. This step is turning the fast key points into a binary representation so that computation can be fast when comparing images. The first step of this is using a smoothing Gaussian kernel to remove the high frequency noise. Then a pair of points in a 31 by 31 patch centered at the key points are compared, and the output either becomes a 1 or a 0, depending on if the intensity is greater than or less than the 2 points. This equation can be seen in the upper right-hand corner. The 31 by 31 patch can be changed depending on user preference. However, the image on the lower right shows a Gaussian 2 spread for the brief algorithm. Each line in this image specifies the 2 points, which should be compared, which output either that 1 or 0 value, which creates the binary vector for the key point. And utilizing the Hamming distance, you can compare vectors between various images to see if they match or not. There's an additional step to creating the rBRIEF descriptor, which simply makes sure that the absolute correlation is the greatest for the key points being used, ensuring that these key points are as unique as possible. Some of the advantages are that it is very computationally robust and much quicker than SIFT as seen in the image in the left. It also doesn't have a patent, so it's free to be used by anybody. Some of the disadvantages are it's not as accurate as SIFT in some other object detection algorithms, and it struggles with scale invariance. It also cannot detect general objects as seen in the YOLO algorithm later on. Below, you'll see some of the images that were produced from our own code. And I will give a short demonstration of the ORB algorithm code. Basically, what's happening is the code will go through a data set of images to see if it can find this Windex bottle within a set of images. There's the second match it found, and that is the third match, and that should be the last match within the images.
All right, YOLO. So YOLO is a type of convolutional neural network. So YOLO stands for you only look once. The idea is that in a still image, we want to put it through a convolutional neural network with some significant modifications we'll discuss in a second. But it looks at all the objects in an image and not only tells what things are objects, what they are specifically, and as well as what is their location relative in the image. So as discussed earlier, we're going to talk about convolutional neural networks since these are everywhere. This is probably the basic form of what YOLO is, and this is where what pretty much makes this possible. Convolution is basically taking an image, as you see in this image here. It takes an input image and then increases its dimensionality by putting through many different filters. It takes a group of pixels and then based on that outputs a singles pixel in the output image. With YOLO, it takes some pretty big modifications to convolution and max pooling and kind of does a whole other thing. So with the interception layer, which is seen in these two images here, basically it does some fancy mixing with the max pooling and does some convolution in a different and even paralleled way so that it deepens the network, but also has some of the images within it become a little bit more sparser and gets each of them into components of a single image. Then it takes each of those images and it puts it through what's a spatial pyramid pooling. This basically takes each of those dense components and puts them into bins, and it so that it keeps the original size of the image and all the information that's in it. And by doing so, it actually improves the performance. The loss function is very different. This is probably be able to tell how poorly you classified all the images, so you can better train this model. Convolutional neural networks, they just have the prediction of classification. So, for instance, it takes into account the centroid, which is this part. Really, no image shows the advantages of YOLO better than this one. It shows clearly that it's able to detect and distinguish one object from another. Like, it's able to tell this guy is different from this girl, which is totally different from SIFT and ORB. You have to almost tell it beforehand that I'm looking for these things, and it can only detect one person or thing in that image. So the disadvantages of YOLO are mainly the data collection is very intense. Here's all the statistics of what data set we use. It's also in training hellaciously time consuming. Running on a GPU, it took over 150 hours to do that. Where with SIFT and ORB, it basically does all the quote unquote training by just giving it a test image. But by far the biggest disadvantage that isn't on this list is that it classifies Harambe as a dog. Let's show you an example of what this looks like in practice. So on Google, I found a picture of pedestrians. But look at this. It's even able to find a car that that you would just never expect it to find it. I didn't even notice that there's a fire hydrant when running this. It's just crazy what kind of things it's able to detect. And that pretty much wraps up this presentation.